All right, so welcome back to Origin Seminars. This is the first talk of this seminars this semester. We have sent out an email about this fall semester schedule, so please send your request to us. And also, if you're a graduate student, please keep your advisors in the loop so that we could actually talk to your advisors as well. All right, so today we have Dr. Emma Whelan from Maynooth University of Ireland. And we will hear about the MHD disk wind component by optical forbidden emission line, spectro-astrometry. This is a really cool topic, and I'm really happy Emma could give us talk about it. So before Emma starts, I would like to remind people this, if you have any clarification question, you could write in the chat, then I will ask that chat question to the speaker. If you have long questions, you can write in chat, or you can wait until the end of her talk where we can have a question and answer session. All right, thanks everyone. And Emma, the floor is yours.
Okay, so thank you very much, and thank you for giving me the opportunity to talk to you. It's the evening here, so this evening. So this is a project with Ilaria Pasucci, and the goal of this project was to try to understand the origin of the low velocity component to the forbidden emission lines we find in the spectra of young stars, and to try to do this using the technique of spectrostometry. And the low velocity component, especially if we think of the oxygen 1 forbidden emission line, has been suggested to be a tracer for MHD disk winds and photoevaporative flows. And so, as you know, MHD disk winds have been suggested as a means maybe by which the angular momentum is removed from the young star, allowing the accretion to proceed. And then the photoevaporated flows are very important for disk dispersal and disk evolution. So both of these things are relevant to how planets form and how our understanding of the architecture of solar systems. So this was an idea of Ilaria's, and she got some time on the VLT using UVIS, the spectrograph UVIS, to do this work. And where I came into it then was due to my expertise in the technique. So this is a technique that I've been coming back to time and time again over the years of my career so far. So since I finished my PhD, and mostly I've used it to study jets and to study brown dwarf jets in particular. But this is my first time thinking about the problem of winds and of disk winds. So maybe I just wanted to give a little bit of background. Okay, so so I'm sure you're all familiar with this picture of the central engine of a young star. So, you know, we're thinking maybe of a T Tauri. We are thinking of a T Tauri star here because the fact that they're optically visible, we can study them on smaller scales. So we have a good picture of the activity in the central engine of the star. We have the accretion flows, and we have the theory of magnetospheric accretion, but we also have winds and outflows and jets, and we can trace all of these things in different wavelength regimes. So what I want to point out here, which is relevant to this talk then obviously, is the disk wind. So we think of of the wind being launched along the disk at different radii. So we have streamlines launched at different radii. And for the purpose of this talk, we can think of the inner part of this disk as being collimated into a jet by the magnetic field. So there are competing theories about how the jets form, and this is just one of them. But this is most relevant to the material that I'll be presenting here. So the inner part of this wind gets collimated into the jet, and then this jet propagates outwards. It interacts with the ambient medium. We get HH objects formed, and we know that these outflows can be many parsec scales in length. So I think 10 or slightly maybe 12 parsecs, if I remember, is the largest Herbig-Haro flow that's been found. But then if we go further out in the disk, we still have a disk wind component. So some of this disk wind remains, and this is what I'm thinking of as the MHD disk wind that may be then traced by the low velocity component of the forbidden emission lines. So does the low velocity component trace the wind? And then we do know that the high velocity component of these lines traces the jet. If we go further out in the disk, even further out in the disk, then we introduce the photoevaporative flow. And it has been suggested, so we think of the work of Barbara Arcolano, that the low velocity component of these forbidden emission lines could be tracing the photoevaporative flow. And so what we're seeing here is the material in the disk is being heated by the UV photons and the X-ray photons from the star, and we're getting a thermal flow. So just a little bit then on the question of angular momentum removal, just to set up the scene for the observations that I'm going to present. So for many years, it was considered that the MRI, or the magnetorotational instability, was responsible for the angular momentum removal in the accretion disks in the young stars. So the disk can become turbulent through the growth of the instability. The instability grows because of the differential rotation and the magnetic field. And because of this, angular momentum is transported outwards, and this enables material to flow radially inwards and for accretion to occur. So this is just an example taken from the work of Jim Stone, and it's actually taken from a recent, a 2012 review by Tom Ray, and it just shows some simulations here of the instability, or the growth of this instability. On the left, then you have the magnetic field lines, or the gold lines. They're perpendicular to the disk. The colors in the disk represent the changing densities as we go out from the midplane in the disk. And what happens is this: the turbulence occurs, this MRI develops, and the angular momentum is transported then through the disk plane. So for many years, this was considered to be the dominant way in which the angular momentum was removed. But then fairly recent studies in 2013 did some more detailed simulations and introduced some disk microphysics and showed that this is actually suppressed in the region where planets form, so where most of the angular momentum should be removed. So to quote from this 2013 paper, they say, "We find that the MRI is completely suppressed, resulting in a fully laminar flow throughout the vertical extent of the disk. And importantly for this work, you get a magnetocentrifugal wind is launched that efficiently carries away the disk angular momentum." And they also give us a very nice test of their theory, because they say that if this is the case, then that the mass loss rate in this wind should be comparable to the mass accretion rate. So the idea is, can we find a tracer of this disk wind? And if we find an observational tracer, can we measure the mass loss rate in the wind, and can we test this theory? So this is the motivation for this work. Okay, so that's just a little bit of the theory, more my area with the observations. So if we just introduce this low velocity component to the forbidden emission line. So these T Tauri stars were first detected in the 1980s, and we saw spectra with multiple forbidden emission lines. So forbidden emission lines of oxygen, nitrogen, sulfur, and many other species. And it was quite quickly seen that in some of these objects, these forbidden emission lines, their line profiles had multiple components. So they were classified into a low velocity component and a high velocity component based on their velocities. So for a velocity, a radial velocity greater than 100 kilometers per second, this is classified as a high velocity component, and then less than 30 kilometers per second, it was classified as a low velocity component. And it quite quickly became apparent that the high velocity component was tracing the jet. You could see this in the spectra. The emission line regions were very extended and very collimated. But the origin of the low velocity component has been debated for a long time. I mean, people looked at the densities, for example, and the radial velocities, and suggested that it was launched in a disk wind. But as I said, there have been other studies that suggested perhaps it's tracing a photoevaporative flow. But is there, only in 2018, you had this paper by Brunel and Nassini, for example, where they conclude that the MHD disk winds are at the origin of both components. But a recent interesting development then in the last number of years was the further classification of the low velocity component into a broad component and a narrow component. And this is based on the full width half maximum of the component. So the low velocity component has a velocity less than 30 kilometers per second. And if its full width half maximum is less than 40 kilometers per second, it's a narrow component, and greater than 40 kilometers per second, it's a broad component. So it can be further divided into a broad component and a narrow component. And Andrea Banzati has done a lot of work on this, and Ilaria And there have been several papers that Ilaria has been involved in. So you can see this kinematical decomposition here for DG tau and CW tau. So DG tau, especially is a T Tauri star that's been very well studied, and its jet has been very well studied. So all of these studies, and I have a list here, there'll be many papers, they looked at densities, radial velocities, the full width half maximum of the lines and the components to try to understand the origin of the different components. So it was concluded that the broad component is likely an MHD disk wind, but the origin of the narrow component is still unclear, and perhaps this narrow component could be tracing a photoevaporative flow. And so what we wanted to do is to apply the technique of spectrostrometry to this problem. With spectrostrometry, you can recover spatial information from an emission line region below the seeing limit generally, or below the angular resolution of your observation. And so could we show that it was tracing either an MHD disk wind or a photoevaporative flow, and could we measure the height of this wind in order to try to constrain the mass loss rates? If we do conclude it's an MHD disk wind, can we measure the mass loss rate and compare it to the mass accretion rate? So this was the problem that we were looking at with this data set that Ilaria got. So to give you an introduction to the technique of spectrostrometry, for those of you who aren't familiar with the technique. So the idea is that you want to fit the point spread function, the spatial profile of a spectrum, in order to measure the centroid of the profile. And then you want to look at how the centroid varies with wavelength. And what you find is that you can find shifts in position at different emission line regions. And so then you try to decipher these shifts and to try to understand what they tell you about the origin of the emission line regions. So on the left here, and this just comes from a paper by Hiro Takami. So Hiro Takami did a lot of the early work with spectrostrometry and studying forbidden emission lines. So what you see is a typical spectrum. The dark band going from top to bottom is the continuum emission from the star, and then you can see your emission line region. I think it's H alpha, perhaps. And what you do is you extract the spatial profile. So you just plot perpendicular to the continuum and fit the profile, which you can see on the right, to measure the centroid. And we typically use this, do this using Gaussian fitting. So this is the simplest way to do it. It can get more complicated, but I'm not going to get into this now. So we consider that we use Gaussian fitting. And if we fit the continuum position, the centroid gives us the position of the star very accurately. So the nice thing about spectrostrometry is that the accuracy to which you can measure the position or the centroid it is dependent just on the signal to noise, really, of your observation. And then when you get to the emission line region, if it's formed in a jet, if it's coming from, if there's actually a companion there that's not being resolved and only one of them is emitting in this emission line, you'll see a shift. If it's in a jet, you'll see a shift in position away from the continuum centroid, away from the stellar position. Or if perhaps, it's tracing a disk, you'll see a shift in position due to Keplerian rotation in that disk. And so that's the basics of the technique. So this is another figure just to illustrate how it works. So this is a spectrum, and this shows the Paschen beta line. So this is taken from a paper that I did during my PhD, and this is DG tau. And these permitted emission lines like Paschen beta in the young stars trace the accretion. They primarily trace the accretion. So if we fit the emission line and with spectrostrometry and compare its centroid to the centroid of the continuum, we wouldn't expect to see any difference because the emission is so close that in the accretion zone that we wouldn't be able to resolve it. So what's shown here is the black points are the continuum and the red points are the emission line. And what I've actually done, so the actual spectrum is shown on the bottom with wavelength along the x-axis or velocity along the x-axis, but what I've actually done here is removed the continuum, and we'll talk about that in a few slides' time on why that's important. What we actually did see for DG tau was that the bulk of the Paschen beta is coincident with the continuum. So for most of the line, the red points are not offset with respect to the black points. But we see this quite large shift of half an arc second in this very extensive blue wing that this line has. And so we were able to show that there was some Paschen beta emitted here in the jet from DG tau. So this is typically what a spectro-astrometric plot, or it's often called a position spectrum, looks like. So on the x-axis we have velocity measured with respect to the emission line of interest, obviously, and then on the y-axis then we have what we call the offset, or the displacement from the continuum position. And in the plots that I will show, we've converted this to AU. And as I said, the nice thing about this is that the accuracy to which you can measure the centroid depends on your seeing, but it primarily depends on your signal to noise ratio, or in this formula here, on the number of detected photons. So if you have seeing of about an arc second, you can, with a large telescope, certainly with the VLT and UVIS, you can quite easily reach a milli-arc second accuracy. Actually with spectrostometry, the atmosphere is your friend. You don't necessarily want good seeing because you want your spatial profile to be well sampled by the size of your pixels. And so also studies have shown that if, for various reasons, if you use a slit width which is narrower than you're seeing, so if your seeing is better than your slit width, you can actually get artifacts introduced into the spectro-astrometric artifacts. So, typically we'll use maybe a 0.6, a 0.8 arc second slit, and we want, seeing of 1 arc second is good enough then in that case. Okay, so as I said, Ilaria got Spectra with UVIS to do this study, and UVIS has been proven to be a particularly useful instrument for spectroastrometry, and it was the instrument that I used to study brown dwarf jets. And the reason why it's very good, it's on a large telescope, so you can get a very high signal to noise in a small amount of time. It can be rotated on the sky, which is really important for the strategy for this study. So you can align your slit at different position angles. So for example, if you wanted to put it along a jet or along a disk or perpendicular to a jet, you can do that with UVIS. And it also has a good, high spectral resolution. So typically I've used it with a spectral resolution of about 40,000, which is about 1 kilometer per second then per pixel. So this was the data that Ilaria got, and the strategy was to perform spectrostometry on spectra taken at 4 position angles. For each source, the disk position angle was the reference for where we were going to put the slits, and I'll show you why we did that. So what do I mean? So you have your accretion disk, and you have your outflow or your wind, or your jet is launched. We can assume it's launched perpendicular to that disk, and generally, they are perpendicular. And what we wanted to do was to place. We wanted to get 2 sets of anti-parallel slits that are perpendicular. So what do I mean? We wanted 1 slit along the disk, and then 1 slit anti-parallel to that, and then 1 slit along the outflow, and 1 slit anti-parallel to that. So if you had a disk that had a position angle of 45 degrees, say, then you'll get a spectrum at 45 degrees, 135 degrees, 225 degrees, and 315 degrees. And that will give you your four spectra that you need. And this, can be done with UVIS. It's not always possible with spectrographs to rotate them on the sky like that, to rotate the slit. And why did we want to do this? So why did we want anti-parallel slits? Firstly, we wanted to remove spectro-astrometric artifacts. So I've found using UVIS over the years that there are no artifacts. I've very rarely seen anything, but there have been studies that show that they do show up with other instruments. So we just mean false signals. So you see offsets in emission lines that are not real. And what we do is that if we take anti-parallel slits, if your signal, your spectroastrometric signal that you're seeing is real, it will invert between the 2 slit positions. So this is an example of one of the spectra that we looked at in the study. It's the sulfur line from Ori Lupi, and we took spectra at 80 degrees and then 260 degrees, and you can see that we see very similar signals, but they're inverted. Okay, the extent of the signals is a little bit different, and this is just to do with some variability in the continuum. So the continuum emission hasn't been subtracted here. So this is one thing about spectroastrometry, is that you need to remove the stellar emission to find the true position of the emission line region. Because when you're fitting it, you're getting a position that's a composite of the stellar position and the emission line region. So what we say is that the continuum drags the position back towards the star. And how it does this, it depends on the ratio between the emission line region and the continuum emission. So if that changes slightly, you'll see a change in the extent of the offset, the size of the offset, which is what I think we're seeing here. It's just some variability, but you can see that the signal is comparable, it's similar, and it's inverting. So this is a real signal. So this is why we use the anti-parallel slits. And what we do is that we subtract the offsets we measure in the anti-parallel slits, and anything real remains, and any artifacts will be removed. And again, this was a method used by Hiro Takami, and so I often refer to it then as the Takami method for removing the artifacts. And the perpendicular slits, we do this because if we have perpendicular slits, we can recover the true position angle of any offset that we measure on the sky. So what do I mean for that? So I'm going to show you an example of one of the brown dwarfs that I studied with UVIS to illustrate this. So this is 2MASS1207A, and it's a very famous source, and it has its 8 Jupiter mass. So it's a 24 Jupiter mass brown dwarf, and it has its 8 Jupiter mass companion. And we got UVIS spectra. We showed that it had forbidden emission, and we were able to show with spectroastrometry that this forbidden emission was offset with respect to the continuum position, with respect to the position of the brown dwarf. And you have to remember that this is a very low mass object. So, we observed for a long time with UVIS, and we got a faint, but their forbidden emission line at very low velocities. But it did have a clear double peak, which on the left here, you can see a position velocity diagram. And I think you can see the 2 peaks clearly in the oxygen 1 line. But the velocities are only about, radio velocities are, less than 10 kilometers per second. But with spectroastrometry, we're able to show that they were offset in different directions, showing that they were in an outflow. And the position angle here of the slit was 0 degrees. And then a few years later, we got another position angle close to 90 degrees. Wasn't exactly at 90 degrees, but we were able to plot the offsets that we measured at 0 degrees against the offsets that we measured at 90 degrees to recover the actual position angle on the sky of this extended emission of the outflow. And you can see here that the blue shifted emission is going towards the east or the northeast, and the red shifted emission towards the southwest. So this is what we can do, and we can make this kind of plot, and this is really important for the results on the disk wind if we have the perpendicular slits. And just another thing to point out here, which becomes relevant later as well, is that you can see here on both sides of this outflow, or we assume it's a jet. And actually, we went on to get images with the VLT, and we found some tentative HH objects along this position angle. So it all tied together. So we can say that it's a jet. But if you see that the highest velocity emission is offset furthest. So the velocity, the emission that has the radial velocity of about plus or minus 10 kilometers per second is furthest from the brown dwarf. And this is a signature of a jet. So the material is accelerating, so you get an increase in distance with velocity. Whereas with the wind, we could expect to see an opposite thing, an opposite gradient, which we do see, which I'm going to show you in a few slides. So this was just to illustrate why we took the anti-parallel slits and why we took the perpendicular slits. So we took the anti-parallel slits to remove the artifacts, any artifacts, and the perpendicular slits to make a map of the position of the emission on the sky, so we could understand what the position angle of the extended emission, any extended emission we find is. Okay, so on then to the actual study. These are the targets that they observed. So TW high, so a couple of transitional disk objects, TW Hydra, T Cha, and then objects with full disks like MP Mus or Ulupi, AS205, which is a multiple system, and T Cra. And the important thing to note here, I think, is that, and this is why I've put this reminder for myself about the D-sharp study, when these observations were planned and the data was found, we didn't have these amazing results for ALMA. So a lot of the position angles of the disks were inferred from modelling and turned out later not to be accurate, especially, for example, or Ulupi. It says here that the disk, or 80 degrees was what was used for the disk PA for the study, but actually it turned out to be more like 120. It doesn't really matter. We get extra information if we do align the slit with the actual disk and jet, but once we have perpendicular slits, we can still recover the position angle of any emission, extended emission that we find. So it's not a disaster, but you just get extra information if you do know the true position angle of the disks. Or of the jets, and then assume that the disk is perpendicular to the jet. Okay, so the first thing that we did then was to extract the spectra, and we looked at the oxygen. We were primarily interested in the 6300 line. We also looked at the sulfur 2 lines, so the sulfur 2 doublet, but we just present the 6731 line here, and also the 01 then 5577 line. And we wanted to look at the different components, and so it's presented in the table here. There's a lot of information here. Some objects were just single components and they just had a low velocity narrow component. Some had a narrow component and a broad component, and then two or Ulupi and AS205 had a high velocity component. And in many of the papers that I mentioned before, where they've done this kind of fitting, there's a color scheme which runs through them all. So the high velocity component is typically shown in green, the low velocity broad component in red, and the low velocity narrow component in blue. So I'll keep to that color scheme here when I show my results. So we found that these sources fell into one of three categories. So we had single component sources, mainly with low velocity broad components, where we didn't detect any spectro-astrometric signal. So the emission was, as far as we could, within the accuracy that we had, was coincident with the source position. And this is MP Mus, T Cha, AS205 South, and TW Hydra. But TW Hydra is a special case. Then we had sources where the low velocity component had been classified as a low velocity component, but it clearly wasn't. It was a jet with a low radial velocity, and so why you get a low radial velocity is because the jet is in the plane of the sky, so it has a low inclination angle with respect to the plane of the sky. And this is T Cran AS205N, and this is important, because many of these sources have been classified in these studies as having low velocity components, and spectroastrometry can, pick out the ones that don't have true low velocity components. And then one source where we did find that the low velocity component, or we did conclude that the low velocity narrow component was tracing an MHD wind. So this is a paper that we just had published recently, and the other results then are going into a second paper. And so this is Ulupi. And what's important here is that we showed for the first time that the low velocity narrow component could be tracing an MHD wind, and resolved the low velocity component in the oxygen in the forbidden emission lines, in the oxygen forbidden emission lines for the first time. So I'm going to start with Ulupi because it's the most interesting. And so I'm going to present all the spectro-astrometric results in this form. So we have the 6300 line on the top and the 6731 line on the bottom. And on the left, we have the first pair of anti-parallel slits subtracted, and then on the right, the second pair. So the left and right are perpendicular to each other. And for Ulupi, we had three components. We had a narrow component and a high velocity component. Previously, the middle component had been classified as a broad component, but we classify it here as a second HVC. So we refer to these as high velocity component 1 and high velocity component 2. So this isn't really relevant to what I want to talk about here. We don't measure any signal in this middle high velocity component, you could say. And the reason we did this was just because the full width half maximum of it was just so large. And so what I've plotted is the spectro-astrometric results. So, the position spectra. So the dark line is without the continuum subtracted, and then the dark points, the black dots, are with the continuum subtracted. So the emission moves further away from the star, as I explained, when we extract the continuum. And so what we can see from this is that the narrow velocity component, the narrow component of the low velocity component, so the narrow component is offset with respect to the star. And you especially see this in the sulfur 2 line. And the high velocity component is as we would expect. And with the perpendicular slits, we see these offsets are in different directions. And this gives us a clue then to the actual offset, the actual position angle, of this emission on the sky. So, and then what I show here then as well, the sigma values just refer to the 1 sigma uncertainty that we were able to reach with the signal to noise that we had in the lines. But I think what is really interesting is when we combine the 2 perpendicular slits to make these 2D plots that I showed already, for the brown dwarf, for the outflow. So what we did is we separated it into the 3 components, and we show them for the high velocity component that's tracing the jet on the left. In the middle, it's the high velocity component that had previously been classified as a broad component, and we don't see any offset here. And then on the right is the narrow component. And so the interesting thing is that the narrow component is offset from the star. It's offset along the same, comparable position angle to the high velocity component. And what I show here actually as well is the red arrow is the position angle of the disk. So you can see that it's perpendicular. No, it's close to being perpendicular to the disk. And the black circles are the uncertainty. So, the position angles that we measure they agree within the uncertainties that we were able to achieve here. And I have no collimation written here. These plots can get a bit confusing because they're not actually telling us anything about the width of the flow. They're only telling us about the location of each velocity with respect to the star, but not with respect to each other, you could say. So, looking at this, it looks like the narrow component is a lot more collimated than the broad component. But this really just reflects the fact that we got a lower signal to noise in the high velocity component than we did in the narrow component. So it's important to remember here that we don't get any information on the width of the flow. All we're getting information is on the position angle of the flow on the sky and how the velocity how the different velocities are distributed with respect to the position of the star. And this is where the idea of having knowing the actual angles of the disk and the jet PA come in, because if we had if we had spectra perpendicular to the disk, along the disk and perpendicular to the jet for RU loopy, we would have been able to use the full width half maximum to get an estimate of the collimation of the flow, to see if the narrow component is wider than the high velocity component, which is what we would expect if it's tracing a wind and if the high velocity component is tracing a jet. But we have future observations planned where I aim to do that. So that's hopefully something I can present in the future. Okay, so as I said, just to summarize, the narrow component and the jet are offset along the same direction with the same position angle and are perpendicular to the disk as we would expect if you have a jet launched and then you have a cone of material in a wind around the jet. But the difference here is in the velocity gradient. And again, this goes back to the example that I showed of the brown dwarf. So if you look at the jet, you can see that the lowest velocities are closest to the star, and the highest velocities are furthest from the star. So the gradient is that the offset in material from the star increases with velocity, as you would expect if the material is being accelerated off the disk into the jet. Whereas with the narrow component, it's the opposite. It has an opposite gradient. The highest velocity material is closest to the star, and the lowest velocity material is further away. And so you can see this more clearly in this plot, I think, which shows it very, very clearly. So we're plotting velocity here on the y-axis and delta z, just height above the disk, on the x-axis. And you can see that in both lines, the jet component and the narrow component have opposite gradients. And okay, for the sulfur 2, for example, you see an initial increase in velocity with distance, and then it decreases. But this is just what we see when you hit a shock in the jet. So this is just a signature of a knot in the jet. So this is the significant result from this analysis of Oriolupi, and this is a very strong signature of a disk wind, we believe. So this allowed us to conclude that the narrow component was tracing the disk wind. We ruled photo evaporation out, firstly because of the velocities that we were measuring. You know, they go up to about 30 kilometers per second in the narrow component. That's too high. But also because we can trace the O1 emission down to about 2 AU from the disk mid-plane. So this means that the wind is launched deep within the gravitational potential well of the star. So it's not a photoevaporative flow. So that's another important result, that in this case anyway, the narrow component is not tracing this kind of wind. To convince ourselves further of this, what we were seeing, we compared our results to a study of the CO emission. So there's the very important paper by Klaus Pontoppidan in 2011, where he did spectroastrometry on the CO line, and this is tracing lower velocities. And it's not offset as far from the star. So what we're looking at here, so just ignore the panel here that says AS205. Basically, there's no similarity between the CO and the forbidden emission lines, the spectroastrometry in AS205. And this I will show is because we're not really seeing a true low velocity component here. So what to concentrate on is Oriolupi. So on the top, I compared the emission line profiles, and they're very similar. And then in the bottom two panels, I compared the spectroastrometry. They took spectroastrometry with CO at slightly different disk position angles. And also the results are not continuum subtracted. So what I'm comparing here is the spectroastrometry in the O1 and sulfur 2 narrow component before continuum subtraction. But what we're seeing is that it has a very similar gradient. So if you look at the 0, you see this initial increase in position and offset at the low velocities, and then this tapering off as we move to higher velocities in position. And so you're seeing a very similar signal here. This in the CO, the sulfur 2 and the oxygen 1, a very similar gradient. And what we think, what we've concluded, which this cartoon shows, is that what we're seeing here is that the high velocity component is tracing the jet, and it's an accelerating jet. So the velocity is increasing. So we're increasing in blue shifted radial velocity as we go from green to blue. And yellow is a lower velocity again. And what we're tracing then in the narrow component are the streamlines in the MHD disk wind. And what we find is that as we move out along the disk, so as OR increases, the velocity is decreasing. It's a Keplerian flow, or it retains some form of a Keplerian flow, and the wind height is increasing. So, and this gives us the signal then, the gradient that we see, the lower velocity emission closer to the star, and the higher velocity emission closer to the star, and the slower material is coming from a streamline further out along the disk at a greater radius, but we measure a greater height due to the lack of collimation in the wind compared to the jet. And so what we think we see is that the sulfur 2 is tracing the inner part of this. It's a bit faster. And then we go further out with the oxygen 1 and then out again with the CO. And this was just a question, just to remind me about a question I got when presenting this work, where they were saying, okay, there does seem to be some initial increase in velocity or in distance with velocity as we go towards the 0 in the narrow component. But if you look at the blue band here, we actually just measure the continuum position, and then there's nothing until we see a component at 0 kilometers per second at an offset of about 10 AU. So I think this gradient is very clear, and this is what we believe we're seeing, and it's this is the model that Pontoppidan used to explain the signal he was seeing in the CO line as well in that 2011 paper. Okay, so this I think is the most significant result from this study. I know I've kept you a long time talking about spectroastrometry, so I'll go through the other results pretty quick. So for the single component sources, I've just shown a sample of the spectroastrometry here in the oxygen 1 line. We don't detect any signal, and I've shown the results here with the continuum, but I've removed the continuum. There's nothing there, and so this material is located closer to the source than the accuracy that we can achieve with the spectroastrometry, and this is a paper that's in preparation. We do see a signal here for AS205S, and this is at about 150 kilometers per second out to a few AU, and this is just a signal due to emission from AS205 north, so the main star in this system, and it has very strong redshifted oxygen 1 forbidden emission. So you can actually detect companions using spectroastrometry as well. T Tauri is an interesting source. So if you look at its line profile, so again, I'm showing the oxygen 1 on top, the sulfur 2 on bottom, the anti-parallel slits on the left, and then the other set on the right, so that the two sets are perpendicular to each other. And this is fitted as having a low velocity narrow component shown in blue, and a red component, the broad component shown in red. But when we did the spectroastrometry, we found very significant offsets. And when we combine them into the 2D plots, what we're seeing here is a jet with a position angle of east-west. And this is actually in agreement with previous studies of the outflow from T Tauri and of where we know what we know of the position angle of the disk. And so all of this emission here is coming from the jet. So if there is a true low velocity component here, we can't see it because the jet has a very low radial velocity. So it's just an example of one that was misclassified from the kinematical studies alone. And AS205N is another example, and this is a very complicated source, because we see, again, two high velocity components, a narrow component, and a third redshifted high velocity component. And we see offsets going in all different directions when we do the spectroastrometry on the different components. So I don't want to spend too much time talking about this because it's quite complicated. Again, we produce the 2D plots and split them up into the different components. So what I believe that we're seeing here, this is known to be a multiple system, and it has three components, it's believed. And I think we're seeing two jets here. So we see one jet which is perpendicular to the known disk position angle of AS205N, and then another component which has a redshifted component that has a low radial velocity. So again, it's hard to tell if the low velocity component is an actual true low velocity component, or it's simply we believe that there's strong evidence that the low velocity component is tracing an MHD disk wind, and it's a narrow component that we're looking at. So this is the first time that we have this kind of evidence for a narrow component, and it's definitely not tracing a photoevaporative flow. we can show that the broad component originates closer to the star than the narrow component. You know, we have a very small sample of one object for the narrow component, and this was predicted, for example, in Andrea's 2019 paper. TW Hydra is a unique case because the disk is face on and we're essentially looking down the barrel of the flow, and spectrostrometry doesn't work so well in that case. And that's a whole other big discussion. By looking at TCRA and AS205N, this shows that the kinematic study alone is not enough to determine the origin of the components. We can misclassify some jets as being low velocity components. And then the mass loss rates are preliminary. We see a greater mass loss rate in the broad component than the narrow component, but we only have one case. We only have Oriolupi. And the comparison between the mass loss and mass accretion is more likely to be at the higher end for Oriolupi. But Oriolupi, I should say, could be a special source. So it has some unique properties. For example, in Andrea's paper, I think it was Andrea's paper, that they showed that the full width half maximum of the components is very high compared to other T Tauri stars. So we wish to extend this work, obviously, to a much larger sample of objects. There's some very interesting objects like DG tau, CW tau, that we really want to observe. And luckily, we got a lot of UVIS time for this semester, so we can add another 8 objects to the sample, and we've picked a few that are like Oriolupi. So hopefully, we can repeat this work and get a better handle on how we could go forward then to estimate the mass loss rates. Okay, so I'll finish there and I'll leave them up. So thank you very much for listening. So if there's any questions.
Thank you, Emma, for a wonderful talk. So if you have a question, could you raise your hand? Well, there were some claps. Okay, so if you have a question, just raise your hand. And I have actually a question. I might have missed it in your talk. For Microjets, if any source doesn't have known, large jets, but there are some sources with a Microjets very close by. Mm-hmm. Do you think they will behave the same way than you would expect it to the bigger, larger jet sources? And what would be, and also the second question is for spectroastrometry, what is the sweet spot of the angles of the disk orientation?
Okay, so for the first question, when you refer to Microjets, are you referring to like the jets from the T Tauri stars? Mm-hmm. So yeah, so these are actually so what we're looking at here are actually Microjets. So yeah, so there's, this term Microjet was used a lot for jets from T Tauri stars like DG tau and Oriolupi, but some of them actually have quite substantial jets. Like there have been studies which have traced the HH objects from these jets and shown that they're fractions of a parsec. So maybe this microjet term doesn't really apply. I mean, we do have some objects then that have the forbidden emission lines, but we don't, if we just look at their spectra or we look at images, we don't see an extended jet. So yeah, I would expect them to behave in the same way if that's the kind of object that you're talking about. I think my feeling here would be that these are just more evolved and they're closer to the transitional disk phase, and the jets are just switching off. But I don't see why we shouldn't see a similar behavior between the two. And then for the spectrostrometry, so do you mean for the sweet spot for measuring the collimation? What the point that I was making? Mm-hmm. If you need to know. Yeah, I mean, you wouldn't want to be off by many degrees, maybe plus or minus 5 degrees. So I don't know if you know these studies where, so people like, say, Catherine Dugadis and Sylvie Cabri, they've used spectral imaging to take images of the jets with AO in different emission lines, and they can measure the full width half maximum of the jets to look at the jet width. and plot it then as a function of distance, and you can infer then that the collimation region of the jet is typically a few tens of AU. So the idea is similar here, that you would make a cut perpendicular to the jet and measure the full width, half the maximum of the emission there, and use it as a measure of the width. But yeah, I think you would need to be pretty close to the position angle of the jet disk system to do it properly. So hopefully, for the sources that we have with the new UVA study, we can do that. We'll have accurate enough position angles.
Right, thank you. And I think Andrea has first question, and then Devanjan and Neo has others. So first, Andrea.
Hi, Andrea.
Hi, Emma. Nice to meet you.
Yeah, you too.
Thank you. Very, very interesting talk. I'm very glad to see. These winds are very complicated, so it's so good to be learning more from the data. I have one question. If you could expand a little bit more on point 2 here. I'm not sure I understand. Now that here you say BC originates closer to the star than the NC, and I was wondering whether you connect to. There was one thing that I wrote in the 2019 paper that I was convinced of and still didn't make much sense, and maybe what you're showing now makes sense of that. Okay. Which is that the BC seem to be closer to the star, but also a higher velocity, and the NC seem to be farther away from the star, but also lower velocity. And still to date, I cannot reconcile this structure. I know that winds have a complex velocity structure that is not only radial but vertical. Too, right? And so one question is on that, if you can expand it. From what I can understand, it's probably connected to the figure you were showing in figure 10 in your paper, where you show a radial and vertical velocity structure. And sorry if I add another, exactly this figure here. And sorry, let me add another question connected to this. Is there any way that we can measure the opening angle of this wind with spectroastrometry? And another thing that I was so convinced of in 2019 in that paper is that there was a signal about at 35 degrees, an opening angle of 35 degrees, but the signal it was not so strong and could be interpreted one way or another. And I was wondering whether spectroastrometry can clarify.
So this is something that myself and Larry puzzled a lot about the data, and I thought I could measure the opening angle, and then I realized I couldn't, and because I just wasn't used to trying to understand winds in the these kind of signals we get from winds. So I suppose in my head I think that the broad component is being emitted from the disk closer to the star, so it has a higher velocity. But it's not reaching the same heights as the narrow component. And then as you go out, you see this narrow component. And this, I don't know. I mean, I've only worked on the observations, and I want to try with the next data set is to do some modeling so I can try to understand it better. But that's how I picture it in my head. And the narrow component is coming from a region very close to the star. So if we go back to Orly-Loopy, I think it was about 0.4 AU was my 1 sigma accuracy. So we could say, it's coming from a region that's probably about 0.5 AU in Z, below, if we're talking about Z, we're talking about height above the disk. And then the narrow component, as we move out along the disk, is getting higher and higher. So it's starting off, it reaches much greater heights than the broad component. And then the question on the opening angle, I think we can do it. And this goes back to Serena's question, but we need the spectra perpendicular to the jet. So because in Orly-Loopy we didn't, Larry assumed that, or took the jet position angle to be 80 degrees. Or the disk position angle, to be 80 degrees. And that came from the modeling that Klaus did in his 2011 Spectro-astrometry paper. And then when the D-sharp study came along, it was 120 degrees. So we didn't have perpendicular, a slit position that was perpendicular to the jet. But if we we have that, what we can do is we can measure the full width half maximum of the narrow component or the broad component in that spectrum, and plot it as a full, with distance along the flow, and we can show that way, we can test that way if the jet is more collimated than the wind. So we can do it for the high velocity component and the low velocity component. And we should see, if everything is correct, we should see a difference in the collimation. We can just, obviously it's just a simple calculation then if we know the width at a particular distance to estimate the opening angle. And this is what they've done. So if you look at especially the papers of Catherine Dugadis, this is what they've done. Or my student just has a paper that came out a few weeks ago with Muse data. So they've done this with spectral imaging. They've measured the full width half maximum of the emission line regions and used this to estimate the opening angles. So I think we can do the same thing with our UVIS data set. So hopefully we can prove that your 35 degrees is correct. And that's really just the missing piece, I think, from this model. We see this very strong gradient, and then it could be the case that RU-loop is just some unusual source, and we don't see this in it's really CW tau and DG tau that we're targeting now, as maybe. But I can tell you that I did spectrostrometry on the high-res data of CW tau, and we see the exact same gradient in the low velocity component as we see in RU-loop. So I'm confident that we're going to see it repeated, but the high-res data we only had one position angle, and so we couldn't do this kind of complete analysis that we've done here. But high-res on Keck it's for spectrostrometry, it's exactly as good as UVIS. So.
Okay, so we have two other questions that maybe you could answer quickly. So first one is from Devanjan, and he asks, is there any possibility that you can detect any of the following elements where there is signatures in the wind following your methodology? Sulfur, and so you can actually zinc, iron, magnesium. You can actually see the chat. Could you answer Devanjan's question?
Okay, yeah. So I think I understand the question properly. So we just need the spectra. It depends on what emission lines you're referring to. For example, magnesium has been looked at in jets with STIS, and a similar technique. It wasn't to look at the extent of the emission line region, but to look for jet rotation in the emission line. So these are papers for Deirdre Coffey, for example. So I don't know about zinc, but all of these other lines, we can detect them. But it's all down to the wavelength that you're talking about of the emission lines and the instrument, if the instrument is good for spectrostrometry.
Okay, next, Neil Turner's question. Thank you, Emma. Is there any spectroastrometric evidence for variability in the wind or jet structure? And I'm thinking of Hubble imaging time series showing blobs moving along the jets from a few stars.
Yeah, you wouldn't necessarily need spectrometry to see that. We see it in the position velocity diagrams of T Tauri stars for the jets. Maybe there's some evidence. So it's another talk to talk about brown dwarf jets, but because they're so small, we don't directly resolve them. So you see variability in the spectrostrometry in the jet. I'm not sure about the winds. I've only looked at RU-loop, but I've never seen this. But it's certainly possible to see variability if you have spectra taken over a few years. And then I think that was it, wasn't it?
Yep. So we went over time, but thank you so much for your exciting talk and result. Is there any other question? If not, we will could you unmute and clap for Emma's talk?
Jay, thank you very much.
Thank you.
Thank you. And we'll make this video available in our website.
Okay, so
I will see you next week.
Have a good semester. Bye.
Thanks.
Thank you.
Bye. Bye.
You too.